This equipment case moves 10 meters across the hangar, then comes 10 meters back to exactly where it started. So how far has it travelled? Well, it's travelled 20 meters, but what's its displacement? 0. Both of these answers are right. They're measuring different things. Distance is a scalar. A scalar has a magnitude, a size, and a unit, but no direction. Displacement is a vector. A vector has a magnitude and a direction. The same distinction separates speed from velocity. The case moves east at 2 meters per second on the outward leg, and west at 2 meters per second on the return. The speeds are equal, but the velocities are different because their directions are different. Any change in velocity means there's an acceleration, and that includes a change of direction. Distance, speed, and mass are all scalars. Displacement, velocity, acceleration, and force are all vectors. Weight is a force, so it points vertically downwards. We represent vector with an arrow. Its length shows the magnitude, and its arrowhead shows the direction. The arrow is not decoration, it decides how vectors combine. Now imagine that two ropes pull the case. One force is 30 newtons east, and the other is 40 newtons north. Adding the numbers gives 70, but that would only be right if both forces were pointing in the same direction. On the physical force diagram, both arrows start at the case. To add them, slide one without turning it or resizing it until its tail meets the other arrow's tip. The resultant runs from the original start to the final tip. Because the forces are at right angles, Pythagoras can give us the magnitude. R equals the square root of 30 squared plus 40 squared, which is 50 newtons. Direction is also part of the answer. Tan theta equals 40 over 30, so theta is 53 degrees north of east. Direct vector addition calculations in this topic use two vectors at a right angle. For another angle, use a scale drawing. State the scale, draw the arrows accurately tip to tail, then measure both the length and direction of the resultant. Resolution runs the same geometry backwards. One vector becomes two perpendicular components with the same effect. If f is at angle theta above the horizontal, the components are f cosine theta horizontally and f sine theta vertically. Cosine belongs to the side adjacent to the marked angle, so trust the triangle rather than a memorized layout. Now move the case onto a ramp. The most useful axes run along and perpendicular to the slope. The ramp tilts, but gravity does not, so the weight W remains vertically downwards. If the ramp is at angle theta to the horizon, the weight resolves into W sine theta down the slope and W cosine theta into the slope. These aren't extra forces, together they replace the original weight. On the flat ramp, theta is 0, so the parallel component balances completely, and the whole weight acts into the surface. Suppose the ramp is smooth, i.e. there's no friction, and a cable pulls parallel to it, and the case moves uphill at a constant velocity. Its acceleration, and therefore the resultant forces, are 0. Tension balances W sine theta along the slope, and with no other perpendicular force, the normal contact force balances W cosine theta. That's equilibrium. An object in equilibrium might be at rest, but it also might be moving at a constant velocity. Constant speed on its own is not enough if the direction is changing. For two forces acting at a point, equilibrium requires equal and opposite vectors. For three coplanar forces all acting at one point, draw the arrows tip to tail. If the last arrow returns to the start, and therefore the triangle closes, the resultant force must be 0. If it doesn't close, the vector from the starting point to the final tip is the resultant force. Or resolve every force along two perpendicular axes, making the components completely cancel out separately. Closed triangle and resolved forces are two views of the same balance. So ask whether direction matters, add the arrows tip to tail, resolve along useful axes, and when forces acting at a point are all in equilibrium, make sure that their arrows close. The numbers tell you how much, the arrows tell you what actually happens. Next, we'll see how a force can turn an object as well as move it.